All right. So when we talk about our reversible reactions, right? Our reversible reactions are those reactions that can go in the forward direction as well as a backward direction. A easy way that you and I can understand this is if we take a look at our copper sulfate crystals. So we just studied acids and bases. So we have talked about our crystals, and we know crystals have water inside of it, right? That is what we studied, that crystals do have some water still present inside of it, and the water that is present inside of it, we call it the water of crystallization. And if we evaporate all of the water, if we remove all of the water, we end up getting an anhydrous form. So that is what we know about. That's what we had studied when we did our crystals. So for example, if I have a copper sulfate crystal and I heat it up, what can happen? That copper sulfate crystal will turn into an anhydrous powder and the water will evaporate away. But if I take this copper sulfate, if I take this copper sulfate that is anhydrous, that is in the form of the powder, and I add water back to it, I can turn it back into, I can turn it back into a crystal. And by the way, this is the test for water. Okay, that whenever they ask you to test for water, you take copper sulfate powder, and in the copper sulfate powder, you end up adding water. And if it turns blue, that means that water is present. So copper sulfate is basically, so this is, in this situation, you can either make the you can either break down the crystal into powder and water, or you can combine powder and the water once again to make your crystal. So what this sort of a reaction is going to be known as a reversible reaction, that it can, you can combine the reactant to give you products, or you can combine, sorry?
And you can combine the products to give
Yes, exactly. Good job. And so this is known as a reversible reaction. And in a reversible reaction, we use this arrow. So this arrow means that it is going to be a reversible reaction. So another example of this is that when you are heating aluminum chloride, okay, that is another example. So if I take aluminum chloride, which is a white solid, and I heat it up, when I heat it up, it will break down into ammonia gas and hydrogen chloride gas. Just want to tell one thing to you, HCl. HCl, when it is in a gaseous form, we call it hydrogen chloride. When the same HCl is in an aqueous form, we call it hydrochloric acid. So that is a difference between them, okay? So if they tell you that hydrogen chloride is being formed, you know that is HCl but in gaseous form. If they say HCl but in aqueous form, so that is hydrochloric acid. So your ammonium chloride can break down to give you ammonia gas and hydrogen chloride gas. So this is happening when you are heating it up. So as you're heating it up, it's going to break down. But as what's going to end up happening, so over here at the bottom is where you're applying the heat. So this is where the heat is being applied. If you go a little bit to the top in this particular area, now the tube is a bit cooler. The temperature is a bit lesser at the top. So what is going to end up happening? The ammonia gas and the hydrochloride gas will combine again to give you your ammonium chloride, and you can see it in the form of your what do you call it, white solid. So you have a white solid at the base where you are heating it up, right? So as you're heating it up, what is happening? It is breaking down into ammonia and hydrogen chloride gas. As the gases reach the top of the tube, the temperature is a bit cooler, and as a result, they recombine with each other, they join back with each other to give you ammonium chloride, and you can see that the white solid accumulates again at the top of the test tube. So this is another example of a reversible reaction. And you can see that the reaction reversed based on temperature. So when we talk about different factors that affect reversible reactions, one of the factors is going to be temperature. So temperature is one of the main things that can cause a reaction to go forward or go backwards. Now, when we talk about reversible reactions, we generally, what we do is that this was not, we generally talk about reversible reactions in a sealed container. This was not a sealed container. This was an open container because your products were allowed to escape, right? Your products were allowed to escape. Now, what happens when I do the same reversible reaction, but I do it in a sealed container? Okay, I'm doing the exact same experiment, but I'm doing it in a sealed container. I'm doing it in an area where no substance can escape. So whatever product is being made, whatever reactant is being made, it is not going to be able to escape, right? It is not going to be able to escape simply because you are doing it in a sealed container. So if the same reversible reaction takes place inside a sealed container, what is going to end up happening? Now, what is going to end up happening is this. We don't need to go into details of it. What it's going to happen is this. We are going to end up reaching an equilibrium, and that equilibrium is known as dynamic equilibrium, right? So whenever you do a reversible reaction in a sealed container in a closed space, you will observe that eventually the reaction is going to reach dynamic equilibrium. What do I mean by dynamic equilibrium? Dynamic equilibrium is that state where the rate of forward reaction is equal to the rate of the reverse reaction. So your forward reaction is also taking place and your backward reaction is taking place, and both of them are taking place at the same rate. So when you reach this particular stage, that particular stage is known as dynamic equilibrium, and this will be observed when you perform your experiment in a sealed container. So what you're basically going to end up seeing, right, is, for example, this is your reaction. Calcium carbonate breaks down into calcium oxide and carbon dioxide. If you do this in an open container, what will happen?
The carbon dioxide escape.
Yes, the carbon dioxide gas will keep on escaping. But when you do in a sealed container, the carbon dioxide gas can combine with calcium oxide to give you calcium carbonate. And eventually, what will happen? The rate at which the forward reaction is happening is going to be equal to rate at which the backward reaction is happening. So when you reach that particular stage where the rate of forward reaction is equal to rate of backward reaction, that stage is known as dynamic equilibrium. And this is what the graph looks like, right? So this is the example that they have given, that this is a blue squares, and these blue squares are turning into yellow squares. Okay. So initially your blue squares are going to turn into yellow squares, and the number of yellow squares are going to start to increase. At one point, so what is going to happen? Let's say initially you had 0 yellow squares, and then you got 5 yellow squares, and then you got 10 yellow squares, and eventually as the yellow squares start to increase, they will start to turn back. They will start to turn back into blue squares. So if you look at the graph, this is what you will observe. You will see that the rate of the blue starts to fall. So rate of the blue square starts to fall, while the number of yellow squares starts to increase, until you end up reaching an equilibrium where the rate of a forward and backward reaction are equal to each other. So blue is representing our reactant and yellow is representing our product. So our initially, if you look at time t is equals to 0, you will see we have no product, right? So at the start, we have no product. That is why the rate of forward reaction is high. At the start, the rate of forward reaction is high because we don't have any product. So of course, how will we have a backward reaction? So initially, the rate of forward reaction is high, but as the reaction proceeds, the rate of the forward reaction decreases. The amount of the rate of your reactant turning into product, the rate of reactant going for the forward reaction decreases. the rate of the backward reaction decreases or the amount of product increases until both of them end up reaching the same rate, and that is going to be known as your dynamic equilibrium. So when we talk about dynamic equilibrium, when you talk about it, there are two conditions that have to be made. One condition is that the rate of the forward reaction is equal to the rate of the reverse reaction. That is one of the properties, okay? That whenever you will have a dynamic equilibrium, the rates will be the same. The second, you can say property of dynamic equilibrium is that the concentration of your reactants and product will be constant. So when you reach dynamic equilibrium, when I reach this particular stage, the concentration of my reactants and products will be constant. I'm not saying they're going to be equal. I'm not saying my reactant will be equal to product. Let that be clear. I'm saying that they're going to be constant, which means that, for example, if the concentration is 1 mole per dm cube, it will stay 1 mole per dm cube. The concentration will not change. That's what I'm saying. I'm not saying that they're going to be equal to each other. Product will have some other concentration. Your reactant will have some other concentration, but the concentrations will not be changing because you are at an equilibrium. The concentrations are going to now remain constant. And this is all going to happen in a closed system. So this is basically what we had to understand about the dynamic equilibrium. So let's go ahead and talk about the position of the equilibrium. That is very important. What is the position of the equilibrium, right? So for example, if you look at equilibrium, I have 90% of reactant A and 10% of my product B. You can see I have more reactant towards the left side because I'm getting a greater amount of reactant. Can you hear me now, Arham?
Yes, now I can. Before I could.
Okay. So basically, what I was explaining to you over here is that I have 90% of my reactant A and I have 10% of product B. So in this situation, you can see we have a lot more reactant as compared to the product. So in this situation, when I'm talking about the equilibrium, I can go ahead and I can say that the equilibrium is towards the left. The position of the equilibrium is towards the left side because I have more reactant rather than product. Like I said, equilibrium does not mean that product and reactant will be equal to each other. It's just that their concentrations will not be changing, but they will not be equal to each other. So the equilibrium is generally towards one side. Either you're getting more product or you're getting more reactant. And this position of the equilibrium can change. You can change the position of the equilibrium to get more product or to get more reactant. So in this situation, you can say that in this situation, you will say that equilibrium is towards the left. It's towards the left side. Why? Because you have more reactant compared to your product. Now, let's go ahead and say you change the conditions. So we will talk about different conditions later on. We'll talk about your temperature. We'll talk about pressure. We're going to talk about concentration and all this. So when you're going to talk about it, let's say that we changed condition, one of the conditions. And by changing the condition, the mixture changed. So now you have 80% of A and 20% of B. So how will you describe it? You are going to say that the equilibrium has shifted towards the right. Okay? Equilibrium has shifted towards the right. So what is going to happen? That is just the terminology. Okay, A is still greater than B. A is still greater than B. If they ask you where is the equilibrium actually present, you will still say that equilibrium, you'll still say that equilibrium is towards the left. But if you compare the two, if you talk about in comparison to the two of them, then you will say that yes, over here, equilibrium has shifted towards the right. So it is still towards the left. It is lying towards the left. but it has shifted a little bit towards the right side compared to this option. So that's how we describe it. When you're answering questions, you say equilibrium has shifted towards the right or the left, whatever the situation is. Now, let's talk about what factors. So I told you we can control different conditions. We can control different factors that can change the position of the equilibrium. So when we are going to talk about all of this, hold on, just give me 1 second. So when we are going to talk about all of this, right? So one of course, the factors is the amount of reactant or the amount of product. So it makes sense that if you increase the amount of reactant, the reaction will go forward. It will go towards the right side. If you increase the amount of product, the reaction will go backwards. It will go towards the left side. That is a bit obvious. Other than that, the ones we have to figure out is pressure, temperature, and a catalyst. Okay, let's talk about pressure. What happens when we increase the or decrease the pressure? What happens when we change pressure? So when we talk about pressure, first of all, let me tell you what happens, and then I will tell you why it happens. Okay, so let's remember this. When you increase the pressure, the reaction shifts to the side, or equilibrium shifts to the side where you have less number of moles. Where you have less number of molecules. So whichever side of the reaction has less number of molecules, the reaction will shift to that side. If we decrease the pressure, the reaction shifts to the side that has a greater number of molecules. For example, on this side, on the right side, I have 2 molecules. 1 plus 1 is 2. On this side, the left side, I have 2 plus 1 is giving me 3. So in this reaction, when I will increase the pressure, the reaction will shift to the side with less number of molecules. So right side has less number of molecules. So if I increase the pressure, the reaction will shift to the right. If I decrease the pressure, the reaction will shift towards the side with more molecules. So you have more molecules on the left side. So if I decrease the pressure, the reaction will shift to the left side.
How?
I will explain to you why. Right now, you just need to, I'll tell you why it happens. But what you need to learn is that when you increase the pressure, it will shift to the side with less number of molecules. When you decrease the pressure, it shifts to the side where you have greater number of molecules. Now, like you said, how or why does it actually happen? So to understand this, we first need to understand what is pressure. So in physics, you might have studied that pressure is force per unit area. If you've done physics, you might have gone over the formula. Pressure is force per unit area. How much force is being exerted per unit area? Now, if I am increasing the pressure, if I am increasing the pressure of the gas, what is going to happen? Remember this, the mixture likes to be at an equilibrium. The mixture likes to be at an equilibrium, right? Because you are in a sealed container. The mixture wants to be at an equilibrium state. By increasing the pressure, we have changed the equilibrium. We have changed the condition. So now what the reaction wants to do is the reaction wants to come back to an equilibrium state. It wants to come back to an equilibrium state. Not the same equilibrium as before, but it wants to reach an equilibrium. So now you have increased the pressure, right? So what's going to happen? The equilibrium is going to shift to the side where there are less number of molecules. Why? Why is it going to shift to the sides where the less number of molecules? The less number of molecules you have, the less collisions with the wall of the container. The less collisions with the wall of the container, the less force per unit area. And because of that, the pressure comes down to an equilibrium level. That is why the reaction will go forward. In this situation, the reaction will go forward. Because when the reaction goes forward, when it goes towards the product side, there are less number of molecules. Less number of molecules means that there are less collisions taking place, which means less force per unit area. Less force per unit area means less pressure. So the value of pressure comes back down. So that is what the equilibrium is going to do. It wants to make sure that, it will change the position. It can go forward and backward to make sure that the total pressure remains the same. Okay. What happens when we decrease the pressure? Now the pressure is too low and the reaction wants to return it back to an original pressure. So what will it do? It will shift to the side with greater number of molecules. Greater number of molecules mean more collisions, more force exerted per unit area, and because of that, the pressure is going to start to rise again and until it comes back to the normal value. So that is why, is that making sense? Why it actually happens like this?
Yes.
So that is why you have to remember where it's going to shift. Increasing the pressure will go to the side with less number of molecules because you have increased the pressure. Now the reaction wants to bring the pressure down. It wants to bring the pressure back to normal. How will it do that? It will say, listen, that side has less molecules. Let's start going in that direction. Less molecules mean that less collisions will take place with the wall. So less force will be exerted. So the pressure will reduce. If it's the other way around, if the pressure is less, when the pressure is less, what is going to happen? They are going to say that, okay, listen, the pressure is too low. We need to start bringing it up to a normal value. So why don't we start going towards the side? Why don't we shift towards the side? But if we get more molecules, so there can be more collisions and there can be more force and there can be a higher pressure. So the pressure comes back to a normal value. Right? So this is how your entire things take place. So increasing the pressure, the position of the equilibrium shifts to the side which has fewer gas molecules. When you decrease the pressure, the position of the equilibrium shifts to the side which has more gas molecules. So for example, this is when you're solving your past papers, you will see this equation very commonly. This equation is the equation for Haber process. You'll probably do Haber process, like in your term 2 or maybe like next year, but it's a part of your Excel syllabus, so you're probably going to do it at some point. Haber process is the process where you make ammonia. You make ammonia using nitrogen and hydrogen. Okay, so nitrogen and hydrogen gas are used to basically make your ammonia. And when you're going to talk about it, this is known as Haber process. In your past papers, in your exams, you'll see a lot of questions about Haber process in this topic. In chemical equilibria, they'll give you chemical equilibria and they will ask you they'll give you this equation and then they will say, oh, what will happen when we increase the temperature? What will happen when we decrease the temperature? Stuff like that, So in this situation, if you increase the pressure, what is going to happen? It needs to shift to the side which is greater number of molecules. So you have 2 molecules on the product side and 4 molecules on the reactant side. So if you increase the pressure, it will shift to the side which has less number of molecules. So that is the right side. So if I increase the pressure, my reaction will shift towards the right side. If I decrease the pressure for the Haber process, what will happen? My reaction will shift to the side which is greater number of molecules. So it will shift towards the left side. Right? So this is basically what happens over here. So this is how they're going to ask you. They're going to give you equations and they'll ask you where is the equilibrium going to shift and explain why it happens. Right? Now, what happens when you have an equation where the number of molecules are the same on both the sides? So over here, you have 2 molecules and over here, you also have 2 molecules. So when the molecules on the reaction side and the product side are the same, pressure will make no difference. So increasing the pressure, decreasing the pressure will have no effect on the equilibrium. because the number of molecules on both the side are similar to each other. Is this making sense?
Yes.
Okay. Then we have to go over what happens on our temperature. Okay. So before we do temperature, you have to know some certain terminologies like exothermic and endothermic, which is the topic of chemical energetics. So when you do it, you will study everything in a lot more detail. But generally, an exothermic reaction
Gives out heat.
Yeah, an exothermic reaction is that reaction which produces heat, right? An endothermic reaction is that reaction which absorbs heat from the surroundings. So when we talk about an endothermic reaction is written with a positive sign, right? If you see that they've written down the value for temperature or they've written down the value for energy, how much energy we need to give, and along with that energy, they've given a positive sign, that means it's an endothermic reaction, okay? And that we need to give this much energy. So if it says 100 kilojoules per mole, that means we need to give 100 kilojoules per mole. If it says plus 100 kilojoules per mole, that means we need to provide. This is the amount of energy we need to provide 100 kilojoules per mole energy so that the reaction can take place. Exothermic reaction is written with a negative sign. So if it says minus 100 kilojoules per mole, that is telling you that energy is being produced, that we don't have to give that 100 kilojoules per mole energy. Instead, we will get this much energy. So this is exothermic and endothermic reaction, and that is how you tell if it's exothermic or endothermic by looking at the delta H values. Delta H simply stands for change in heat energy. Or when you will do the topic in detail, you will study a term known as enthalpy. Enthalpy is the same thing as heat energy. So change in enthalpy. Okay. The change in enthalpy or change in energy is this much. So if it says with a negative sign, that is exothermic. If it says it with a positive sign, then that is endothermic. Now, when we talk about this reaction, so generally they will, in the exams, they'll give you your reaction, and in front of the reaction, they will write down your value of enthalpy change, or they will write down your value of heat energy change. Okay. Now, the value that they give you is generally for the forward reaction. So for example, if it says delta H minus 100 kilojoules per mole, this value is for the forward reaction. That means what does it tell you? Automatically. Automatically, when we write down, whenever they give you a value in the exam, that value is for forward reaction.
Means during the reaction, 100 kilojoules per mole is being produced.
Yeah, exactly. In the forward reaction, not the backward reaction. But when the reaction is going forward, 100 kilojoules per mole energy is going to be produced. It's going to be released. So remember this, both the reactions are opposite to each other. So if the forward reaction is exothermic, that means that the backward reaction will be endothermic. Yeah, so they're opposite to each other, right? So the values given in the questions are for the forward reaction. So in this situation, you will say that the forward reaction is endothermic, which means that backward reaction is the endothermic one. So forward reaction is exothermic. So backward reaction must be endothermic. So that is how you're going to go ahead and write down to figure out who is forward and who is exothermic and who is endothermic. So the one they have given you the value for, that is the forward reaction. So in this situation, forward reaction is exothermic, backward reaction is endothermic. So what is going to happen when we increase the temperature? When we increase the temperature, the reaction will shift to the side that is endothermic. And if we decrease the temperature, the reaction will shift to the side that is exothermic. So in this situation, in the situation they've given us over here, if I increase the temperature, the reaction will shift to the endothermic side. So the forward reaction is exothermic, backward reaction is endothermic. So that means if I increase the temperature, the reaction will go to the endothermic side, that is the backward side. So the reaction will shift towards the left. If I decrease the temperature, the reaction will go towards the exothermic side. Exothermic side is the forward side. So if I decrease the temperature, my reaction will shift towards the right side. So this is how temperature is actually going to work. Making sense?
Yes.
And what is the reasoning for it? Why does this basically happen? So this happens with the same reason as pressure, because you want to return it back to a normal value. So just like that, you wanted to bring the pressure back to a normal value. So the same thing you need to do over here. You need to return the temperature back to a normal value. So if the temperature has decreased, the reaction will shift to the exothermic side. So heat is produced and the temperature comes back up to normal. If the temperature is too high, what will the reaction do? The reaction will shift to the endothermic side. So the temperature is used up, the heat is used up by the endothermic reaction, and the temperature falls down. So it's the same thing. You want to bring it back to a normal value. So that is why you are shifting it accordingly. So that is the effect of temperature. Let's talk about a catalyst. A catalyst has no effect on the position of equilibrium. It has no effect on the position. It will not make it go forward. It will not make it go backward. It will not make it go left. It will not make it go right. It will simply speed up the reaction, and it will speed up the reaction. It will speed up both forward and reverse, forward and backwards. Both the reactions are going to basically speed up at the same time in the same amount. That is why there is no effect of the catalyst. That is why catalyst does not produce any change in the position of equilibrium, simply because the forward reaction and the backward reaction, both of them will speed up by the same amount. So when you add the catalyst, they will both increase by the exact same amount. There's going to be no change in the overall position of your equilibrium.
Means it will make it to equilibrium. Means
Sorry?
it will make it closer to equilibrium. It will try to make it constant, right?
Yeah, exactly. So it will basically affect, yeah, it will basically affect both. It will affect the forward as well and the backward as well. So when it is affecting both the reactions, then of course there will be no result, right? Because forward is also happening, reverse is also happening, and both of them are speeding up. So when both of them will speed up, they will speed up by the same amount. So there is no change effect of a catalyst on the equilibrium. So let's go ahead and take this particular example. This is your nitrogen oxide, and this is your nitrogen tetroxide. Okay. So your nitrogen dioxide can join together with each other to give you nitrogen tetroxide. Nitrogen dioxide is brown in color. Nitrogen tetroxide is colorless. Now, let's go ahead and discuss what will happen. So tell me, Arham, if I increase the pressure over here, what do you think will happen? To which side is the reaction going to shift if I increase the pressure?
It will increase both of the sides. Oh.
Pressure and temperature will cause the equilibrium to shift. The only one that has an effect on both the things is catalyst. Catalyst will speed up both the forward reaction and the backward reaction. But pressure and your temperature have an effect. They will make the equilibrium go to a certain side. So do you remember what did I tell you? When you increase the pressure, where does the equilibrium go?
It goes to it shifts to the place where lesser molecules are present.
So in this equation, where do you have lesser molecules, left or right?
They both are same.
Are you sure? Take a look again.
Right?
Right, exactly. Look, you have 2 over here and only 1 over here, right? You have a 2 written next to NO2, right? You have to take a look at this number as well. This number is important. So you have 2 over here and just 1 over here. So that means the right side has got less number of molecules, left side has got more molecules. So when I increase the pressure, my reaction will shift to the which side?
Right.
Right. And what will happen if I decrease the pressure?
Then do the equilibrium will shift to the left side to the greater
Good
mass
job.
of molecules.
And what will you observe? What will you see from your own eyes? When you increase the pressure, what will you see?
Like I see, then there will be more colorless gas present.
Yeah,
Like it will be
the
transparent.
brown color is going to be lighter. That's how you can say it,
Okay.
because you can't see colorless, right? You can't say I see colorless gas because you don't see colorless things. You simply say that the brown color is going to become much more lighter. And what will happen if I decrease the pressure?
The brown, like it will be
Yeah,
more brown, it will increase.
you will see a more intense brown color, or the brown color will become darker. Now, what will happen if I increase the temperature? So think about it. For that, you need to figure out what is the forward reaction. What do you think is the forward reaction? Do you think the forward reaction is exothermic or endothermic?
It's endothermic.
Are you sure?
No, it's exo. Yeah, it's
It's
minus.
exo. Whenever you have a negative sign, it is always exo. Negative means that we don't have to give in the energy, it is producing energy. Okay, so that is exothermic. What does that mean about the backward reaction? What do you think the backward reaction will be?
Endothermic.
Endothermic. So the backward reaction will always be forward of the backward reaction will always be opposite of the forward reaction. So now in this situation, do you remember what I told you? When you increase the temperature, where does the reaction go? Exothermic or endothermic?
Endo.
Endo, right? Because you want to bring the
Yeah.
temperature back down, right? So you will go towards the endothermic side so that the energy is used up in the reaction and the temperature falls. So which is the endothermic side, left or right?
Um, left.
Left. So the reaction will shift to the left. What happens if I decrease the temperature?
It will shift to the right side, will turn to
Yeah,
exothermic.
exactly. It will shift to the exothermic side. So it is going to end up shifting towards the right side. So this is how you're going to solve the question. So if they say what happens when we increase the temperature, what will you observe? You will observe that the brown color is going to become much more darker. What happens when you decrease the temperature? We will observe that the brown color becomes a lot lighter. So this is basically how you're going to figure these questions out.
Okay.
So that is what you had to do related to your topic of reversible chemical equilibria, reversible reactions. Okay. Now, let me go ahead and share some questions with you, and let's go over a few questions and practice those. Just give me 1 minute to share with you. So this topic, when you do in the past papers, is often linked with your Haber process, okay? Because Haber process is it's also a reversible reaction, so they often link it to the Haber process, right? So you will see questions that are mixed up with the Haber process as well. But I don't think your teacher is going to give that. Do talk to your teacher and ask whether the questions of your Haber process will be included in the topic of chemical equilibria. If they are going to be included, we will go ahead and cover them in a bit more detail. If they are not included, then we don't need to spend a lot of effort on them. Just give me 1 second. Let me share this with you. Okay, take a look at the first part. Iodine reacts with chlorine to form iodine monochloride. Write a chemical equation for this reaction. So just write down a general equation. They have told you everything, what the reactants are, what the products are. You just have to write down an equation and balance it. That's it. So go ahead, give that a try. You want to write it down on the chart, you can do that as well.
Yes, isn't it already balanced?
Are you sure?
I2Cl2 and 2ICl.
Good job. Now that's correct. I2 plus Cl2 is going to give you 2ICl. Now they're saying iodine monochloride reacts reversibly with chlorine to form iodine trichloride. The reaction mixture is allowed to reach a state of dynamic equilibrium. One feature of a reaction is that is in dynamic equilibrium is that both forward reaction and backward reaction occur simultaneously. Give two other features of a reaction that is a dynamic equilibrium.
The concentration will be constant.
Yes, the concentration of the reactants and the products will remain constant. Another thing,
And I don't know.
the other one is that the rate of forward reaction and rate of backward reaction will be equal to each other. Okay, so there
Oh,
one feature is that forward reaction and backward reaction occur simultaneously, which means that they occur at the same time. The second, another feature is that the rate of forward reaction and rate of backward reaction will be equal to each other, and the concentration of the products and the reactants will remain constant. When the equilibrium mixture is heated, it becomes dark brown in color. Explain whether the backward reaction is exothermic or endothermic.
It's endothermic.
Good job. And how will you explain it? What is the reasoning you're going to give?
Because it returns to its dark brown color, it starts to turn dark brown
Yeah.
because when
Mhm.
it gains heat.
Yeah, you don't say it gains heat. What you will state is that when the temperature increases, the reaction shifts to the endothermic side. You will use the exact statement. In your explanation, you can give the exact statement. When the temperature increases, the reaction shifts to the side that is endothermic. Since the color is becoming darker or the darker brown color appears, that means the backward reaction must be endothermic.
Okay.
Okay, now see, this is what I meant, that they often mix it with ammonia. Ammonia can be made by reacting nitrogen and hydrogen in the presence of an iron catalyst according to the equation. The reaction is reversible and the mixture can, if left for long enough, reach a position of dynamic equilibrium. The graph shows how the percentage of ammonia at equilibrium depends upon the temperature and pressure used. So you look at the graph, this is the pressure on the this is the pressure of ammonia at your y-axis. This is pressure of the environment, okay? On the x-axis, you have pressure of the environment. This is the pressure of ammonia, this ammonia product. And then you have different graphs for different temperatures. So they're saying state two features of a reaction mixture that is in dynamic equilibrium.
Say two features.
Mhm.
One, the concentration will remain constant, and second, the rate of forward and backward reactions will be the same.
Good job, that's correct. Now they're saying use the graph to state the effect on the percentage of ammonia at equilibrium of the following changes: an increase in temperature and increase in pressure. When I am increasing the temperature, what do you think is happening to percentage of ammonia at equilibrium? When I'm
It's
increasing the
decreasing,
temperature, it
decreasing.
is decreasing. And what is happening when I'm increasing the pressure?
It will shift. The equilibrium will shift um to the place where more molecules.
Right. So what is that? What's that going to do to the percentage of ammonia? You can just take a look at your graph. Looking at the graph, what do you think is happening to percentage of ammonia as you increase the pressure?
As we increase the pressure, the percentage of ammonia decreases.
Increases, exactly. So that's what you will see. Explain why these changes have the effects you have given. Now you have to explain your answer. So you said when you increase the temperature, the percentage of ammonia decreases. So why do you think that is happening? Why is the percentage of ammonia decreasing when you increase the temperature?
I don't know the temperature one.
Sorry, Anna, what are you saying?
I am sorry, I don't know the temperature one.
Okay, tell me, forget the graph. You don't have to use the graph to explain. Use your equation to explain. Tell me, if I increase the temperature, what will happen? Just look at this equation and tell me. When I will increase the temperature, to what side will the reaction shift? Exothermic or endothermic? When you will increase the temperature, where will the reaction shift? To the exothermic side or the endothermic side?
Exo?
When you increase temperature, to what side does it shift? Normally, generally, what did I tell you? If you increase the temperature, to what side will the reaction shift? Exothermic or endothermic? In the lecture, when we went over the lecture, what did I tell you? When you increase the temperature, to what side does it shift? You told me the answer correctly in the previous question.
Endothermic?
Yeah, it will shift to the endothermic side so that so what is going to happen when you're going to increase the temperature, the reaction is going to shift to the endothermic side. Now, which reaction is exothermic and which reaction is endothermic? What is the forward
The
reaction? What do
forward
you
one is exo and the backward is endo.
exactly? So that is what you have to explain over here. You will say that when I increase the temperature, the reaction shifts to the endothermic side. Since the endothermic side is the backward reaction, that is why the amount of ammonia will decrease. That is why the amount of product will decrease, because the reaction is shifting backwards. The equilibrium is shifting towards the left, because when I increase the temperature, the reaction goes towards the endothermic side. Since the backward reaction is the endothermic reaction, so the amount of ammonia will decrease. Now, is it making sense?
Yeah. Yes.
Now tell me, what was the effect of pressure? Why is it that when you increase pressure, the amount of ammonia increases?
Because it shifts to the because when we increase the pressure, the equilibrium shifts to the place with lesser amount of molecules.
Good job. Exactly. So you will say that, yeah, when you increase the pressure, it will shift to the side with less number of molecules.
Which
So the
is true and
right side has less molecules. You're correct. And then what else can you say?
and if the pressure will be decreasing, then it will shift, the equilibrium will be shifted to the place which with larger number of molecules, like
Yeah, that's fine. Fine. So right now you have to explain why the amount of ammonia is increasing. So what do you think? When you're increasing the pressure, the reaction is shifting towards
the right side, so more
right
ammonia
side.
will be produced.
Exactly. So that's how you'll explain it, that when I'm going to increase the pressure, the reaction will shift to the side with less number of molecules. So the reaction will shift to the right. And as a result, more ammonia will be produced because now there is more forward reaction. Okay. We don't have to deal with this. This is related to Haber process, so we don't. Okay, this is related to moles. So let's do moles calculation because we have to take a look at our mole calculations. Okay. Now they're saying the equation for formation of ammonia is this. Calculate the amount in moles of ammonia that could be formed in the Haber process from 112 kilograms of nitrogen, assuming all nitrogen is converted into ammonia. So all nitrogen is being converted into ammonia. You have 112 kilograms of nitrogen. So you have to calculate the moles of ammonia. So you have to calculate the moles of ammonia. This is what you have to calculate. The moles of ammonia. You have to calculate the moles of ammonia. And you have the mass of nitrogen.
Mole is equal to mass over mass of 1 mole.
Yes, good. That's a good start.
So like 112 over 14.
Uh-huh. 112 over what? Sorry, can you say it again?
14 maybe.
14. Are you sure it will be 14?
No, 14.
Yeah, I'm saying, are you sure it will be 14?
Uh,
That's exactly what I'm asking. Are you sure it will be 14?
I mean, that's like the molar volume of.
That's the mass of one atom of nitrogen. Take a look at the formula of nitrogen gas.
Oh, okay, sorry.
Yeah, exactly. So you have to take a look at the formula of nitrogen gas. The formula of
28.
nitrogen gas is N2.
28.
Yeah, exactly. So you'll have to multiply it by your 28.
No, miss,
So
it's divide.
sorry,
It's divide.
Yeah, I mean
Mass.
14. Yeah, 14 multiplied by 2. That's what I was saying actually. That you will multiply it by 2 and you'll get 28. And then after that,
4. Answer is 4.
1 minute. Did you notice something else in the question?
Uh,
Can you read the question from here to here?
Calculate the amount in moles of ammonia that could be formed in the Haber process from 112 kilograms of nitrogen, assuming all nitrogen is converted into ammonia.
So did you notice something? Did you take a look at your units? Units given to you in the question.
It's kilograms and
It's kilograms. So you have to turn your kilograms into grams, because remember, when we use the formula N is equal to M over MR, the mass is in grams. So you have to change your kilograms into grams as well.
okay. It's 112,000.
Exactly. So then divided by your 28. So what does that give you?
4,000.
4,000. Now, the answer you got, 4,000 Arham, is for your nitrogen gas. What will be the number of moles of ammonia?
We can
What?
compare the equation.
Sorry?
We can compare the equation or
Yeah, you will definitely compare the equation. You will always compare the equation.
okay.
Did you figure it out?
Hmm.
Okay,
Can we
look,
use
yeah. Yeah. What will we use?
we will can we use this h as like x to find it? Or
Okay, look, so what you can do over here is this. Look, you have one of nitrogen and ammonia, correct? So you have one of nitrogen. Can you see that in the equation? There's a
yeah.
2 written next to ammonia. So that's how you're going to solve it. Okay. So you have 2 of ammonia and 1 of nitrogen. So what are the number of moles of ammonia? Because the number of moles of
X.
nitrogen are 4,000. So this is how you will solve it. Okay. So there are 2 molecules of ammonia and only 1 molecule of nitrogen. So what will be the number of moles of ammonia, that is X, when you have 4,000 moles of nitrogen? So you're going to write it down like this. On the top, you will write down ammonia, what you have to find. And on the bottom, you will write down nitrogen. And then you will simply solve for X. So what answer will you get?
X is equal to 8,000.
Good job. So its answer is going to be 8,000. So that's how you're going to solve the question. Okay. So Arham, we're going to go ahead and we'll stop it over here.